Okay, so here we have a connected graph. You can get to everywhere from everywhere. Again, that is not a vertex in the middle. That's, again, like an overpass. So if it's a completely connected graph, the only theorem Hamilton has is that there will be n-1 unique circuits for him. And again, remember, Hamilton cares about He cares about vertices. He cares about the cities. Edges could care less. So I have 1, 2, 3, 4. 4 minus 1 factorial, 3 factorial, which means 3 times 2 times 1. So there are 6 unique ways of doing this. And so what happens sometimes is there's kind of like, if you think of these being a flight, like the cost to fly from A to B or A to C or A to D. So like Atlanta to Chicago or Atlanta to Detroit or Atlanta to Baltimore. If we kind of look at those prices, this is kind of where this comes in real life. So say we have some flights here. These are all one way. I'm just going to put some money on those diagonals. So 124 going that way and 155 going that way. All right, so with this method, we know there's 6 unique ways. We got to find them all right? So, you might be like, okay, if I start at A, B, C, D, and back to A. And you're like, okay, so A, B, C, D, and back to A. That would be a circuit, okay? Another one might be A, B, D, C, A. So A, B, D, C, A. I could go A, C, B, D, A. A, C, B, D, A. Now I found 3. I know there's 3 more. So there's A, C, D, B, A, D, B, C, A. And what's left? A, D, C, B, A. And once I find all 6, then I'm good. All right. So in real life, what the brute force method of figuring out the cost of like what it would be to fly all these flights and get back home would be list out all 6 possibilities and then do the math. So like, for example, A to B costs what? $190. B to C costs $126. B to C. C to D costs $179. And D back to A is $157. And I would add that up, and that would be the cost of that trip, okay? And I would do that for all of these. So for like the next one, I go, okay, A to B is $190. But instead of going to C, I'm going to D, which is $155. From D, I'm going to C, which is $179. And from C, I'm flying back to A for $124. And so what you would do in the brute force method is you would figure out the cost of all these flight plans and then pick the cheapest one. Okay, that is called brute force. Okay, that can take a while. If, like even with a computer, like this is in your book, if you have a connected graph with 18 vertices, okay, this is how many circuits there would be. That means you move the decimal 14 jumps to the right. It would take a computer 3.7 days to do that math, to figure out which one's the best one. Notice if you have 23 vertices in a connected graph, it would be 1.1, and again, you'd move the decimal and add zeros, or tack on zeros, 21. So you move it once and have 20 more zeros. That would take a supercomputer like 35,000 years. So, even for a computer, that is a lot of possibilities. So that's kind of a hard sale, so to speak. So we have this other one, and again, this goes to Hamilton because we're dealing with cities, like getting to different cities or traveling. And this is called the Traveling Salesperson. But basically what you do is you pick the cheapest route as you go. So the Traveling Salesperson, okay, you just pick the cheapest route as you go and then you get back home. It doesn't guarantee the cheapest, but it does guarantee not the most expensive. So here, the way to find the cheapest is actually list them all out, do the math, figure out which has the cheapest price. And again, if you have like 10 of them, I mean, even a supercomputer is going to have a hard time doing that. So if humans are going to do it, and we have a lot, it's probably better just to do the Traveling Salesperson, where you keep picking the cheapest until we get home. And again, remember, this goes with Hamilton. So we only have to get to every city, and then we don't get home. So, okay, I had to edit a little bit there, so if it glitched, I'm sorry. All right, so if we're going to go back, let's go back and do this method with Hamilton. And say we want to start with city A, because say we live in Atlanta, so we don't want to start somewhere else. So say we're at A, and we don't want to list the brute force method and figure them all out. We just want to pick the cheapest as we go, which is Traveling Salesperson. So notice that's my cheapest to begin with, $124. So I'm going to go from A to C, and that cost me $124, okay? And so from C, I have to pick the next cheapest, which between $179 and $126, I'm going to go with the $126. So now I'm to B, and that cost me $126. Now notice at this point, you don't always have a choice. Even if this is cheaper, I can't go back to A because I have to get to city D. So regardless, I'm going to pick the 155. Even if it happened to be the most expensive, doesn't matter. I have to get back. And then I'm going to get back to A, which is what, 157. So sometimes at the end, you don't have a lot of decisions. And so then what you would do is you'd add up the 124, 126, 155, and 157, add up those prices, and that would be the flight, the cost, okay? Now, my guess is it's not going to be the cheapest, right? Like if we list them all out, there might be a better one, but this is fast and a human, you know, we can kind of do that. All right, I'm going to pause for a second. We'll do another one. Okay, here's another connected graph, which again, with brute force, you'd have to list all the possibilities and then use that n-1 factorial and then, you know, list out all the prices, okay? But that takes too much time. So we're going to do what's called nearest neighbor, and we're going to start at A. And so from A, we're going to pick the cheapest one, which it looks like 114 is the cheapest. So we're going to go down to C, and we're going to write down the price of 114. Okay, from C, the cheapest is 115 up to E. So I'm going to take 115 price. So add up 115, and now we're at E. It's a 5. All right, from E, it looks like the cheapest is 128 to get back to A, but you can't go back to A because you have to get everywhere else yet. So what's the next cheapest? Probably what, 194? So I'm going to take 194 to D. From D, I don't want to go back to C. I have a choice of 145. Can't get back to A anyway, so I'm going to have to take 145 to B. And from B, I just have to go back home to A, which again, 180 might not be the cheapest, but I have to get back home, okay? And so when you're done, what you do is you add up all those prices, okay? So you're going to add up 114, 115, 194, 145, and 180, and the cost of the trip is $748, okay? Guaranteed not to be the most expensive, but probably not the cheapest. So the only way to get the cheapest is to do every possibility and do that whole brute force method, okay, which can be challenging. All right, a couple things again, just a quick review if you have something like this. If you're doing Euler, look at the degrees. So 1, 2, 3, 1, 2, 3, 4. Let's see what's the degree. This one's, I'm going to move this up just a little bit. This is 3, 4, 2, 5, 2, 1, 2, 3. That's 4, 1, 2, 3, 4. Let's see, what do I have? Do I have 2 odds? I have 2 odds. So where is I have exactly 2 odds. So it has a path but no circuit. Okay, so I'm going to be looking for path, and again, probably a good idea to start at one of my odds. It just gives you more transportation. So let's see, if I'm doing him, I want to touch everyone, right? So if I go to A to F, F to G, G to E, and I'm doing Euler, so I care about edges, edges, edges. So I can go back, I can backtrack. So I'm going to go back and pick up F, and I'm going to go up and pick up D. I cannot cross over the edge again. Then I'm going to go back to A. All right, from A, I'm going to go over to B. And again, I'm going to repeat D again. I could care less. This is Euler. He cares about edges, D to E. And then let's see, E to B. B to, what is that, B to C. And I finally got back C to E. Okay, it's a path, I started at A, ended at E, but I touched every edge. And again, there's multiple answers on that. That's just one, okay? But that's if I'm doing Euler, okay? What if I'm doing Hamilton? Hamilton has no lovely theorems, so there is no piece of paper that you can look at. You just have to try it. And so with Euler, again, I think starting at an odd is always a good idea. So, or I mean with Hamilton. So let's look at Hamilton. If I start there, get a piece of paper in here. All right, so if I start at A, all right, then what? So I start at A. I want to get to every city. So usually going around the outside is a good idea. So A to F, F to G, G to E, E to C. I'm just hitting the outside to B, and then I could go to D, and I actually can get back to A, okay? So that one, I could actually do the outside, which is usually a good idea. Just take these outside paths, and then at the last minute, I can go in, and I can actually get back, okay? Again, I did not touch every edge. That's fine, because he cares about vertices, like flying to every city and then getting back home. All right, hopefully that helps. And